So can you see the slides?
Yes, we can.
Okay, thank you. So hi, everyone. Thank you so much for the opportunity. It's a privilege to be with you in this symposium, although online. Today, I'm going to talk about the neutrinos from muon-rich ultra-high energy electromagnetic cascade. At the beginning, I will give a brief introduction to the electromagnetic cascade development and what is considered as a common conventionally electromagnetic cascade. And then I will talk about some concepts and parameters that are crucial in the cascade development, like inelasticity. Then I will go to the ultra-high energy stage. I will discuss the subleading photon-photon and electron-photon interactions and the possibility of neutrino production during these interactions. Then I will introduce a Monte Carlo simulation named MUNIECA to calculate the neutrino spectrum. At the end, I will show some results for the neutrino spectrum from the electromagnetic cascade at the ultra-high energy stage. So first of all, let me begin with a simple, basically, scenario, the electromagnetic cascade at the cosmological distance propagation. We know that any astrophysical source, like most of the astrophysical source, can emit gamma ray, electron, positron, neutrino, gravitational wave probably, or cosmic ray. We know that the neutrinos can reach to the Earth directly, but soon after the discovery of the CMB, it was noticed that the cosmic ray at the ultra-high energy regime can interact with the background photon field, the CMB, and go through the delta resonance, producing charged pion and neutral pion. And then it was noticed also that the photons from the decay of the pi zero can interact with the CMB photon and initiate a phenomena called electromagnetic cascade, which has been scrutinized by Brzezinski and Smirnov in 1975 as a handle to probe the cosmogenic neutrinos. By the cosmogenic neutrinos, I mean the neutrinos from the charged pion decay, which is called the GZK effect by Grice and Zatzpin and Kuzmin. It was noticed. But what I want to talk about today basically is that it is a general case that any high energy photon emitted by an astrophysical source can interact with this background photon CMB and initiate the electromagnetic cascade. But what is the electromagnetic cascade? It's a successive iteration of electron pair production and inverse Compton scattering. And why it is a successive iteration, basically, it is coming from the fact that the fraction of the incoming leading energy that goes to the outgoing particle is large in each of these interactions, somehow that at each sequence of EPP plus ICS, sorry for using the acronyms because I think it takes time to use the complete name. At each sequence of the EPP plus ICS, the leading particle emerges with energies close to the initial. For example, imagine an initial photon, a photon injected at the energy, a photon or electron injected at the energy 10 to the 20 electron volt, interacting with the CMB photon with energy 10 to the minus 3 in a head-on collision. The inelasticity, which is the fraction of the energy that goes to the emerging particle at the end, for both of these interactions is more than 90%. However, it is more useful for our calculation that to introduce an average of this quantity, the inelasticity, as you can see in this relation. Basically, this relation is giving us an average of the inelasticity. So this emerging with the energy close to the initial energy, this means that the whole scenario can repeat again. And the electromagnetic cascade basically will be developed. But the point that I want to make is that at the ultra high energy stage, specifically at the energies larger than the muon pair production, center of momentum energy squared larger than 4mu squared, the situation will be more complicated because other channels for photon-photon and electron-photon interactions will be open up. Here in this slide and the next slide, I have provided a list of photon-photon, subleading photon-photon and electron-photon interactions. Like we can have double pair production, muon pair production, electron pair and muon pair production, radiative corrections to these interactions, charge pion pair production, neutral pion pair production, and other hadronic processes also. Also, for the electron-photon interactions, we can have electron-muon pair production, electron triplet production, which in the literature is known as triplet pair production, and radiative corrections to inverse Compton scale. The point is that whenever we have a charged pion or muon, these particles can decay to the neutrinos, and then we will have a neutrino spectrum from the electromagnetic cascade. But the question is that what is the relevance of these interactions? Basically, I mean, how much energy from these interactions during the cascade development will channel to the neutrino? Is it significant or not? And what is the effect of this microphysics on the cascade development? Also, I should mention here that some of these interactions are already basically taken into account in some numerical calculation, some of the codes like CR-propa. CR-propa is taking into account double pair production and triplet pair production or electron triplet production in the cascade development. However, no interaction, no neutrino generator interaction is included. So to answer the questions that I made, it is useful to look at the mean free path or interaction length and comparing it with the energy loss length. By the energy loss length, I mean the scale that the emerging particle will lose its energy significantly, which is defined by this relation, as you can see. In this plot at the right side, you can see I'm comparing the interaction length, the energy loss length of electron pair production with the interaction length or mean free path of double pair production, muon pair production, and charge pion pair production. And you can see that the energy loss length of electron pair production is getting larger than the mean free path of MPP, muon pair production, and DPP, double pair production. And at ultra high energies, it's almost getting equal to the charge pion pair production up to the Born approximation. Basically, this line is for the charge pion pair production at with the first Born approximation. This means that before the electron or photon, the emerging electron or photon loses its energy significantly, we have the chance of MPP or DPP happen. Also, in these plots, you can see the interaction length of electron triplet production, inverse Compton scattering, and electron muon pair production. As you can see at the energies like 10 to the 17 electron volts for the cosmological distance propagation, the electron triplet production is becoming dominant over all of these interactions. But the point is that for the electron triplet production, the inelasticity is so high, or in another definition, is so small that the outgoing electron from the electron triplet production takes almost 100% of the energy of the incoming electron. So basically, that doesn't change anything at the ultra high energy stage. So the competition will be between the inverse Compton scattering and electron muon pair production. Something that I should mention here, that is these lines in these plots are universal lines. Basically, the energies multiplied by 1 plus z, and the length is multiplied by 1 plus z cubed, which gives us a universal plot for any redshift. They can be applied, and you can see the horizon for example, for the redshift 10 at the top of the plot. Another point is that the cascade also can happen inside the astrophysical sources, although it is very model dependent. It depends on the models that we have for the astrophysical sources. For example, imagine an active galactic nuclei, the supermassive black hole at the center, the corona of the source. With the current models that we have, we know that it is possible to have a thermal X-ray, and then the gamma ray from the synchrotron radiation can interact with this thermal X-ray and produce electromagnetic cascade. So this is another case that the electromagnetic cascade, basically, if the center of momentum energy squared of the electromagnetic cascade is larger than muon pair production, it is possible to produce neutrinos. So all in all together, we know that having all of these interactions, the nature of the electromagnetic cascade is stochastic. So a Monte Carlo simulation can be useful for solving it. For this reason, we have written a Monte Carlo simulation in a Python 3 framework named Munieka, muons and neutrinos in high energy electromagnetic cascade, consists of 4 photon-photon interactions, basically electron pair production, muon pair production, double pair production, and charged pion pair production, and 2 electron-photon interaction, ICS and EMP. In Munieka, basically, the double pair production that we have used is a new double pair production, basically a new reassessment, a new numerical reassessment of double pair production, both in differential cross-section and in the inelasticity. Also for the EMPP, we have used a new numerical reassessment. Also, Munieka will give us the neutrino spectrum, both in the case of cosmological distance propagation and inside astrophysical source. As I said, it is model dependent, but inside the code, there are a place to set the options for the source. For example, the temperature of the background photon field, the spectrum of the background photon field, etc. So in some situation, you can have the neutrino spectrum also inside the astrophysical source. The algorithm of the code is a simple Monte Carlo simulation. Basically, at each step of photon-photon interaction or electron-photon interaction, the code is calculating the probability of each interaction with respect to their cross-section. And then using their inelasticity, it's calculating the energy of the emerging particles. It saves the neutrinos, and then the electromagnetic part again will be injected into the code for developing the cascade. So at the end, I would like to show you some results. For example, for the case of cosmological distance propagation, as you can see, for a photon with the energy 10 to the 21 electron volt at redshift 10 injected to the code, you can see here in this plot, the red line is showing the neutrino spectrum from the electromagnetic cascade and comparing it with the basically conventional scenario of the cosmogenic neutrino production from the pion decay. As you can see, at the high energy, it is not dominant. It is suppressed by the conventional scenario, the neutrino spectrum from the electromagnetic cascade. However, at lower energies, it's become dominant. The feature is that the peak of this spectrum is extended, for example, for this energy and redshift, the peak of the spectrum is extended around 3 orders of magnitude. So it becomes dominant over the conventional scenario for 2 orders of magnitude, for example, here at the low energy. The other plot is showing basically the number of each neutrino generator process occurrence in 5,000 realization of the code. For example, you can see around 30 times muon pair production, 10 times electron muon pair production, and a few times of charge pion pair production has happened. I should mention that the number of charge pion pair production may be different because we are just taking into account the firstborn approximation, so a complete numerical reassessment of the cross-section of charge pion pair production is needed to have a better image of this interaction. Another case was inside the astrophysical source. For this one, as I said, it is model dependent. We compared the result of the Munieka with a leptonic model for the NGC 1068 proposed by Dan Hooper and Catherine Blant. In this plot is from their paper. They are basically calculating in a leptonic model, which is basically the electromagnetic inside the astrophysical source. A synchrotron radiation is interacting with the background X-ray, thermal X-ray, and producing this neutrino spectrum, and they are feeding basically this neutrino spectrum to the spectrum that we observed from NGC 1068. And in this plot, actually, you can see in the red line what we have obtained from Munieka, which is almost consistent, but there are some differences. Basically, this difference is coming from the fact that they haven't considered, they just considered muon pair production in their calculation. No DPP or CPPP or EMPP is considered. Also, the inelasticity of the muon pair production is just taken into account 0.5, and multiple muon production is neglected. So basically, in a complete numerical calculation, we will have this red line from Munieka. And basically, you can see here a schematic picture of the model that is considered. The magnetic field is 5 kilogauss, and in the corona of the source, the synchronous radiation can be calculated interacting with the X-ray background with the temperature of 1 kV. It's a thermal X-ray. So this is the model basically that we have calculated, with the total power injected above 1 TeV being 1.2 times 10 to the 43 erg per second. At the end, I want, as a conclusion and recap, I would like to say that a pure leptonic process is inside the electromagnetic cascade for neutrino production at the ultra energy regime, which 20 to 30% of the injected energy channels to neutrinos. And I just introduced Python 3 framework to calculate the neutrino spectrum from the electromagnetic cascade. Of course, the detection of the ultra-high energy neutrinos, basically in the case of cosmological distance propagation, the detection would be with the upcoming experiments like GRAND or IceCube Gen 2. As a future and application of this work, I would say that we need a next version of Munieka, basically a full set of non-negligible hadronic processes specifically for photon-photon interactions is needed with all of the non-trivial cross-section for the hadronic processes. Also, the magnetic field is neglected inside the Munieka. Basically, all of the calculations, all of the results that I've shown is without any magnetic field. So magnetic field, we know that is playing a crucial role, and we know we need to add the magnetic field inside the code. However, as an application, this neutrino spectrum from the electromagnetic cascade will help us to probably put a limit on the population of supermassive black holes at high redshift. I mean, the redshift between 5 to 12, 13. And also inside the, for example, inside the calculation of, inside the, basically, when we put limits on the super heavy dark matter lifetime, this neutrino spectrum is neglected. So I estimate that taking into account this neutrino spectrum would change something like a coefficient of 2, the lifetime that we have with respect to the neutrino experiments. And at the end, I would like to thank my collaborators, Antonio Capanema, Arman Smiley, Pasquale Serpico, and this talk was basically a summary of these two papers. And thank you.
Thank you. Thank you very much, Amir.
Sure.
Any questions in the room?
Hi, thank you very much. I was wondering about the case that you showed on the case 1. What assumptions did you make about the emission? So starting photon emission and the pi emission, is it
This case.
in this case, yeah.
Okay. So it's just a photon injected at the energy 10 to the 21 electron volt at the redshift 10, interacting with the CMB.
Only one photon. So one would, if one wanted to study the.
No, basically not just one photon. Basically, many realization. It's a Monte Carlo simulation, right? So something like 5,000 to 10,000 realization or photon is injected inside the code, and then here is the result.
Thanks.
Yeah. Thank you.
Thank you. Very nice work. Just, I'm curious about I don't know if you have had the opportunity to investigate what is the photo production of neutrinos inside AGNs or jets. And that is because there has been some work about the photo production by taking into account the interaction with the matter in these plasmas in these places. What do you know would be more important for the production of neutrinos in this case? The interaction with electromagnetic fields or with the matter inside these AGNs and plasmas or the jets?
So basically, I'm not expert actually in this field inside the AGNs, but what I know is that there are some models that basically in these models, active galactic nuclei is producing ultra high energy cosmic rays inside the jet, and it's emitted to the universe. So basically, these cosmic rays are of ultra high energies, so they can interact with the CMB, and then the photon from the pi zero decay again can go to the electromagnetic cascade and produce neutrinos. In another case, inside the corona of the source, as I know, it doesn't need to go to the ultra high energy stage, because already the energy of the background photon field inside the active galactic nuclei is high, like it's extended to the X-ray. So at the X-ray, the photons with the energy something like 10 TeV or order of TeV, 10 TeV, basically again these photons have the situation to produce neutrino during the electromagnetic cascade. In fact, I haven't calculated that which one is dominant, or basically these two spectrum are in two different energy regimes. Basically, one of them is in the high energy in the PeV or 10 PeV regime. The other one would be around TeV. So basically, but I haven't calculated. Basically, it depends on the model. And also it depends on the magnetic field inside the source, because the magnetic field, it is possible that the magnetic field reduce the energy of the high energy photons because of the synchrotron radiation. So, make problem for the electromagnetic cascade development. But I haven't calculated it exactly so that what will happen. This is one of the things that I'm working on currently, right? Actually. So I cannot say exactly what is the result, but yes, these two are the two different regimes, energy regimes. I don't know if I answered your question exactly or not. Please let me know if you have any other question.
Okay, no problem. What I understand is basically that there is still work to do, and that basically
Yes.
shining with neutrinos.
Yes.
Any other questions in the room or online? It doesn't seem so. Thank you. Thank you again, Amir.
Thank you so much for the opportunity. Thank you.